Today we're going to be talking about some of the basics of machine elements. So continuing off our solids lecture from a couple weeks ago, we learned pretty much the basics of stress strain, how that relates to certain material properties, what kind of a typical stress strain relation looks like, and just some of the ways that we detect failure. So I guess machine elements differs a little from solids in the sense that we're not really looking at the material properties, or we don't care too much about what goes on at the molecular level. Really what we're just looking at is how do we build systems that satisfy our requirements. So you have a lot of standard types of systems such as bearings, shafts, and those kind of really standard setups. So machine elements kind of deals with how you select materials, how you configure these systems to behave in alignment with your requirements. Okay, so I guess I wanted to start off with material selection. So we discussed a little bit about how different properties of materials manifest depending on what kind of material it is. So a really common pitfall I see in LHRE in particular is when we ask you guys to define requirements, material related requirements, the first thing I always see is weight must be minimized or stiffness must be maximized. So I've always thought that's kind of like a backwards way of looking at the problem. Everyone kind of jumps to weight and density as the standard material requirements because those are really freebies, right? They're pretty well known. And most of the time, if you have stronger material and less weight, it's better for your system. So those are always the two requirements that we see. But there's a lot of other considerations that you miss out if you kind of just jump to those conclusions that, oh, there's some kind of material that is best for this scenario just based on weight and strength alone. In reality, there's quite a few other variables which we'll talk about that should go into your thought process when you're selecting a material, and those extend way beyond just weight and stiffness. So every time I ask myself how I want to start a material selection process, I always start with the system requirements. So in any given part on the car, whether you want to do a free body diagram for the whole car or analyze just a single isolated part, a lot of people either jump to FEA or they basically build up the whole assembly in FEA and try to say, oh, this material is better because it deflects less or something like that using FEA. But I think it's a lot more important to define your loading conditions even outside of that, right? Let's say you have something like a bell crank. It seems like a relatively innocent part. You just have a pivot and a couple of loading points. And you would think, oh, I just need to choose a material that's stiff and strong. But that single part undergoes complex loading conditions. You can have cyclic loading on the part, and you can have really high peak loading if your tire hits a really large bump. So I always start answering the problem by asking the questions of what kind of loading conditions is it going under. And there are a lot of different ways you can consider this. You have static dynamics, just specifying what kind of conditions the system operates under. And you can also define the fixtures and conditions. For example, if you have if you have a pivot that isn't constrained in terms of the moment, it can be loaded extremely differently than if you have a moment supported beam. So defining those fixtures beforehand and those loading conditions is really important before you select the material. Additionally, you have some systems where there's some kind of complicated kinematics going on. Let's say the control arms of the car. The system can change in shape quite a bit, and as a result, the loading can change. So it's important to understand how to assess the system at every point in its operation. And of course, you also have things like fatigue, where the part undergoes repeated stresses as opposed to a large peak stress, and stiffness requirements. There are some cases where you actually want less of a stiffness. As Robert knows, the blade for the suspension last year was a way of adjusting the roll stiffness of the car. So in some instances, you want to be able to actually have a lower stiffness than a higher one. So all of these unique, I guess, design needs that you need should be identified before you even go to material selection phase. So in terms of needs, how do you actually express this as a material need? Well, there are usually a few properties that map really well to a design need that you need for a given part. For example, we talked about high peak loads in the bell crank. In that case, it's really simple, right? You just look at the yield strength and it either satisfies your requirement or it doesn't. And you can get a little more complicated with this in terms of if you have a shaft, which is supporting a pretty large moment load, you need a relatively high hardness. So then you would look to something like the Brunel hardness. So we're going to be going through each of these properties at a high level, just talking about what you need to look at, not necessarily all the theory behind it. But I just really want to drive home the fact that you should always start with the requirements, and very naturally the materials requirements that you need kind of fall out of that. Okay, so yeah, from a pure yield standpoint, this is typically the first thing that you look at when you select a material. You just look at the yield strength, where again, the yield strength is the stress at the point where the part doesn't return to its original configuration. It's plastically deformed once you load it past that point. And other really common ones to look at are the Young's modulus. So typically you really just design around the yield stress. You find the peak stress in your system and you just make sure that it's under your yield stress by a certain amount. And that's the most basic material requirement that you can have, and basically something you look at every time you select a material. Another really common one is the Young's modulus. So we talked about how the proportion of these lines on the stress strain curve, the slope, relates to how stiff the part is. So it doesn't necessarily map one-to-one with how stiff your part is going to be, right? Depending on the strength of your material, you might need to design the part in a different shape than had you selected another material. So in that case, the stiffness doesn't necessarily correspond to the stiffness of your part, but generally the stiffness of the material is the lower bound on how stiff you can make your part. So that's an important thing to consider. For really high peak loading conditions, you might also think about how much energy can my part actually take before it passes the yield point. So we had already talked about it a bit last time, so I won't go into too much detail, but you have these integrals of the stress strain curve up until the elastic limit. So that's basically asking the question of how much energy can my part absorb before it permanently deforms. Okay, so I think this is a pretty interesting plot to demonstrate why we choose certain materials for certain applications. So on the left, we have a plot of the density versus the Young's modulus. So density versus stiffness. And again, this is like a super common requirement. So metals live kind of in this region. Does anyone have a guess as to why we would use metals as opposed to like a polymer in this case? High Young's modulus, sure. But it's also high density. So like, why do we want both high density? So it's a loaded question. So it's like there's some materials like ceramics that have a higher stiffness but lower density, right? So per the standard LHRE requirement, it should be the better material. Why don't we just make everything out of some kind of ceramic? Yeah, so this is kind of the pitfall of only choosing like 2 parameters to select a material with. You kind of forget some of the other important properties. So ceramics are bad in some cases because they're brittle. So they have a really high yield strength, but they don't have much energy that they can absorb before they basically permanently just separate, right? Something else you can do is take advantage of the fact that metals are still ductile after the yield point. So if I were to make ceramic control arms and they somehow broke because I did my calculations wrong, my car would just, I don't know, fall on the ground and like it could injure someone, right? Whereas if you use a metallic part, after the part yields, you can detect it. The deformation is usually pretty obvious, but it isn't a critical failure. So this is another kind of hidden reason why metals are preferable to something like ceramics, even though this plot seems to imply that you would always want ceramics. So it's always important to recognize like the interplay between all these different parameters. So I think this plot kind of makes a kind of generalized way of how these different parameters interact in metals. So in general, as you heat treat a material, you can essentially get it to be in different phases. And this is a question of material science, but the way to think of it is that there are internal phases and grains in the material. And by heat treating it, you affect those phases, even though the chemical composition is for the most part the same. So by heat treating materials, you can gain access to different relations between these properties. So in general, the tensile strength and the yield strength, unsurprisingly, always correlate to each other. But as you'll notice, the Brunel hardness of the hardness of the material also goes down as the tensile strength and yield strength tend to go down, which kind of makes sense. In contrast, as you anneal or heat treat a material in any way, in general, if you make the material stronger, you're also going to make it more brittle for metals. So that's the most important relationship that you should be aware of. In some cases, you'll need the enhanced yield strength, but in some cases, you want the ductility for reasons such as you have, I guess, detectable failure without it being too critical. So whenever you look up a material, not all materials will be made the same, even if you call it steel, right? You have the standard alloys or the chemical composition. So if you see something like 1020, that's referring to the percentage of carbon within the metal and the alloying metal that they use with it. So all those codes are a little confusing at first, but all you should understand is there's certain alloys that you can put in metals to change their properties, but there are compromises, right? So 1020 has a relatively, I guess, high carbon content, so it might be a little more brittle than one with less carbon content. So this is also, this is pretty similar to the previous plot, but it gives us an idea of why we choose some materials rather than others. So let's see, do we have anyone from Aero here? Aero, okay. So I've got a question for you. Why don't we use metals for our wings? Why do we use composites? Sure. What else do you, like, what are the, if we go back to the slide. Yeah, so if we go back to this slide and you look at the design needs, which of these do you think would be important to an aero component? Yeah, sure, right. So your wings are designed to provide downforce so that you don't have to add weight to the vehicle that you have to accelerate. But if it weighs too much, obviously that's not going to be beneficial to the car in net, right? So that's probably your first requirement. What would you say is like a secondary requirement? Yes, you're right. It does undergo a lot of cycles, but in this case, the loads on the wing are typically so small that they're not enough to fatigue the part. It's a bit tricky, but I would argue stiffness is the second one because the geometry of the wing is so critical to how it operates that if it's flexible, it's not going to behave the way that you want it to, and you get effects such as buffering, etc. So in contrast, if you look at something like the suspension, you would still want a similar property such as high stiffness, right? But you're not really going to care about the weight, I would argue, as much because a lot of the components are so small that you care more about something like the peak loading and the number of cycles as opposed to the other requirements. So in kind of like a holistic sense, that's why we choose different materials for different systems. They have different fundamental requirements. And if you can see it from a really high level, that makes you a lot better to, in a lot better of a position to select a material. Okay. So yeah, that other property, hardness, that we talked about. In general, this is kind of measured in a, I don't know if I want to call it a sketchy way, but it's basically just a practical test when you're determining the hardness of materials. There's a machine that looks like this, which has an indenter. It's basically just a cone-shaped piece, and it pushes into the material at different loads. So you have something called the minor load, which is initially to see how much the materials formed under this initial load. And then you have these other conditions where you have the minor load plus the major load, and then just the major load. So by measuring the distances between this minor load and the major load, this is mislabeled, it should be major load, you can determine the hardness of the material. So this is like its susceptibility to deform under contact stresses. So something like hardness is really important in scenarios where you have these high contact stresses. Some of the hardest materials you'll see if you just look around at household items are bearings. They have really high contact stresses since they have roller elements and there's contact stress on like a spherical or a cylindrical element. So those balls or cylinders in the bearings typically have to be really hard, and the material is selected as such to do that. You'll also see really hard components or materials in areas where you have fastener joints. So fasteners can actually deform against each other where you have the mating thread and the fastener. If the material isn't sufficiently hard, then you get deformation of the thread as you load it. And in general, just really small interfaces between highly loaded parts. So on the car, you'll see that anywhere you have like a fastener, like on the push rod, for example, that's really heavily loaded. So the important thing to realize with hardness is it really only has relative scale. So I won't look at a bearing and be like, oh, I need, if I'm designing a bearing, I won't look at the scale and be like, oh, I need this. It's generally like what material is reasonable for this application and has a relatively higher hardness than another, because this test is in a way kind of subjective. And there are different types of these tests. The most common one is called the Brunel hardness test, but there's a couple other ones. And if you see those names, you should just realize like they measure certain things and you just kind of read up on the test and look at that relatively. Okay, so another really important thing that we encounter on the car is fatigue loading. So in contrast to just peak loading, where you have a really high static load on a part, which is what most people tend to design around, fatigue loading is something that's relatively innocuous, but can really creep up on you. So I think about 4 years ago, we had designed a hub where it had, the hub is what supports the wheel load. So it had this really sharp corner where the bearing interfaces with the abutment. So as the car drives, there's a normal load on the wheel that pushes up on it. A relatively high normal load, like just at static, it's the weight of your vehicle roughly divided by 4, right? So as the wheel actually rotates relative to the hub, which is spinning, that moment load is actually rotating around the hub. So this isn't super obvious because you don't typically think of loading like in the frame of a rotating part, but because this hub is rotating, even though the normal load, like relative to our inertial frame of reference, is stationary on the wheel, it's actually rotating on the hub. So they didn't recognize that. And what happened? It fatigued that joint. You had the concentration or the combination of a really high stress concentration with a repeated load from the wheel rotating. So even though the part looked like it had a factor of safety of 4 in the FEA, if you're not careful about these things, then that fatigue loading causes failure, I think, in like 1,000 cycles, so 1,000 rotations of the wheel. And for something like a car, that's just like not acceptable, right? So really innocuous thing where they chose the right material, but because they didn't design the geometry right and didn't recognize the aspects of fatigue loading, it caused the part to fail really critically. I think they had like 2 days to machine it before they went to comp. So not a really good scenario to be in. The what? Yeah, the undercut on the, well, there was no undercut. It was just a straight cut. Yeah. So fatigue in general occurs because not all materials are homogeneous. You have something that you might recognize is called a grain structure within metals. So as I alluded to before, metals typically, when you make them, are not homogeneous. They have these regions of different chemical composition or just physically different bound atoms, which are called grains. So in general, the reason fatigue originates is because you have what are called slip regions between these grains. And those slip regions are areas for stress to concentrate. And essentially, you can kind of think of fatigue as gradual damage in a part. As you exacerbate these slip boundaries, over time, they form cracks on, rather than a micro scale, as you see in stage 1, it'll grow on a macro scale, and the crack generally propagates more and more until you have the stress geometrically concentrating at a given point. And this concentration causes the part to eventually just fail. And a lot of failure analysis actually goes into looking at these failure surfaces. Like I could look at 2 parts that I've separated and look at the grain boundaries, and you can tell how it's failed and damaged over time and when it eventually failed. So the most typical way to quantify fatigue loading is you just have an axis of number of cycles versus, the number of cycles versus failure, right? So for different parts, they're going to have different strengths. And the most common test is what's called the purely reversing stress. So this is where you have a part and the amplitude of the stress is fully reversed in amplitude in either direction. But it's important to also recognize that, this is the plot where you have the fatigue strength on the left side and the number of stress cycles. And the interesting thing is that certain parts have this kind of asymptote where if you stay within under a certain amount of loading, the part will actually never fail, which is kind of counterintuitive, but it's a really unique property of steel. You wouldn't get something like that in aluminum. I don't know the chemical reason why, but it's just important to recognize that there's something called the fatigue limit, where if you stay under it, the part will never fail no matter how many cycles you undergo. In the converse, if you're in this region where there is a finite point of failure, the higher your reversing load, then the lower the number of cycles you can get to before the part fails, right? That's pretty straightforward. What some people don't recognize is that it's not just the alternating stress that you need to consider, but also the mean stress. So in practice, when you have manufacturers who are trying to, I guess, tell you about the fatigue ratings of their materials, you'll get something like this. It's called a mean stress alternating stress plot. So the idea behind that is that you have two components typically of loading, some fair amount of mean stress. So let's say I take a rod and I just pull it a static amount of stress, and then an alternating stress. So that's the reversing component on top of that mean stress. So in combination of those two, you get different properties. And this plot is a little different, but these are basically isolines on the number of cycles. So let's say my part underwent 1,000 cycles. This mean stress on the left side is if I have this point right here. So if I have no alternating stress, right? That's just a pure mean stress. So this is coincidentally just the ultimate failure fatigue, sorry, the ultimate tensile failure point on a material. Whereas on the left side, this is if you were to purely alternate the stress. So no average component. And in that case, you also have a different failure point. So you can have different combinations of mean stress and alternating stress along this line that cause failure at the same number of cycles. So it's always important if you have a large mean stress component to also consider that on top of it. And so ultimately, we have to have some way of predicting whether a material is going to fail at these given loading conditions, right? So there are a few different criteria that have been developed, I guess, by material scientists over the years. And it's essentially limit lines on this mean stress and alternating stress plot. So you can plot these lines just as an approximation without, I guess, having exact testing data for the material. So these dots are actually like how the material would fail if you tested it some n number of cycles, right? But you can predict it using these different equations, which produce either the dotted line or the straight line. And it's not too important to know the names, but typically the Goodman criteria or the straight line is a really good way of assessing if you're going to fail under fatigue. So as long as you're under this region and this triangle here, then you're good. Okay, so we've talked a little bit about material selection from the standpoint of several different properties. So these properties manifest, I guess, in interesting ways in very common types of systems. So there are, for any of you familiar with bearings, there are several different types, right? You have a straight roller, which is pretty common, where there are cylindrical elements which separate an inner and outer ring. And in general, when you see a bearing, it's going to be constructed of some kind of inner ring with a really hard material, since that's what interfaces with your part, and an outer ring. And it's typically very precisely machined because you care about things like how much play the bearing has and how stiff it is. So these different bearings are all solutions to kind of solve this problem. And the way I like to think about bearings is kind of from a pressure on each individual roller element standpoint. So if we look at this first example, you can see that the line of contact between the cylindrical bearing rolling element and the two shells is a line, right? You have a straight surface here, but this roller is of a smaller radius, so only contacts in a line. So what happens when you have a stress on a purely like line element? It's infinite because the line has no area. So depending on the type of contact that you have between the roller element and the shells, you can get different amounts of pressure on the roller elements. And because this pressure is different, it actually manifests as different stiffnesses in the bearings. So let's say I took a sphere and I were to take a plate and push against that sphere. So for the initial part, I have a stress concentration basically in a point on the sphere, right? And I have an infinite stress, even though I have a finite force that I'm pushing on it with the plate. As I push further and further, that sphere is going to deform and the contact area changes from a point to a circle of area. So that circle of area is now distributing my stress across the bearing. And the interesting thing is that the stiffness of that joint is actually changing as I do that. So the harder I push, the lower the pressure, even though the same amount of force, right? So the stiffness of the system actually goes up as you deform it more. So this is really how bearings behave as well, right? If I were to take a radial load on this bearing and push down on this element, even if it's spinning, in general, if I have a larger area of contact, it's going to be stiffer, right? So these different type of bearings just have different configurations that are designed to take certain types of loads. So in this cylindrical roller element type, if I were to apply, I guess I should define the different types of load first. So in general, there are three types of loads that you want to react with bearings: radial, axial, and moment loads. So the radial loads push basically normally to the bearing surface, whether that's originating from the inner ring or the outer ring. Moment loads are where you have, I guess, a moment applied to either of the rings, and axial loads are where the load is in this direction, in the same axis as a whole. So for example, the straight roller bearing here would be relatively poor for reacting axial loads. Why is that? I've just got this really tiny area of contact right here between the roller and the cups, right? So really high stresses, really poor at reacting axial loads. So let's look at a different one, the tapered roller bearing. And this, incidentally, is actually what we use for our supporting our hubs in the car. So you'll notice that this one has a roller element that's at a diagonal. So what does that do for you? Well, it turns out it's really good for reacting axial loads and moment loads in contrast to the straight roller bearing. So these elements, now that my load line or my line of contact between the outer ring and this roller element, it's now not, it's oriented kind of between the axial direction and the radial direction. So if I were to push radially, I can still support some amount of load because a component of that is going into the reaction against this roller element. But now axially, I also have a relatively large area component, right? So this can actually react axial loads, which again is a system requirement that you would define ahead of time for your wheels. When you corner, there's a lateral force on your wheels. So obviously the bearing supporting that has to be able to support that lateral load, right? So that's kind of one example of how I would choose a bearing based on the requirements that I have. This one is also much better at reacting moment loads than, for example, the straight roller. Again, because you have these two surfaces that are a component in both directions, if I were to apply a moment to either of these cups, I now have a line that reacts it much better than if I just had a straight roller in this direction, which can only react radial loads. So when we select bearings, another really important assessment to do is the amount of cycles that it can undergo. That's really what you want a bearing to do, right? Support some minimum amount of radial, axial, and moment load. And by quantifying how many of those loads you have over what kind of alternation over its lifetime, you want it to survive a certain number of revolutions. So typically the bearing manufacturers will define this in two ways, or one of two ways. They'll specify the number of revolutions of the inner ring until you have evidence of fatigue, or the number of hours of use at standard angular speed. So the evidence of fatigue that you typically see in something like a bearing failure is what they call galling. You can have some kind of foreign material, or sorry, you have debris that builds up in the bearing as you damage the surfaces, and over time, this results in damage of either the cup or the roller elements to the point where they don't function anymore. Foreign debris, I guess, isn't really something that they do, but these are relatively standard tests that the bearing manufacturer carries out. I don't know exactly how they inspect it, but the idea is that you just stay under their load rating and you should be fine. So if you go look at a bearing, or look at a bearing catalog, it's pretty intimidating at first. It'll typically look something like this, where there's just a whole bunch of rows and you're just like, I want it to support some kind of load. Which one do I choose? So there's two constraints that you usually want to consider. You're usually pretty space limited in terms of the size of your bearing. Just to use suspension again as an example, because I'm familiar with it, or unsprung, where you have the hub, it's constrained by the size of the wheel, right? You have to fit this whole rotating system inside of your wheel diameter while supporting a relatively large load. Okay, so we start there, and you kind of have some minimum amount of size that you need to stay under. So you can select typically the radius of the bearing first, and that's kind of the first thing you do. The second thing you should ask is, what kind of loads do I need my bearing to support at static? So for the wheel, that's pretty simple. You have a moment load that originates from the peak normal load that you expect on the wheel, but you also have these lateral loads that push on the tire and these longitudinal loads. So you can see that even though the bearing only has three basic loads, radial, axial, and moment loads, the way that they manifest from the loading conditions on your system can be pretty complicated. And like, we haven't even really figured that out, right? So let's say we wanted to drive a car, I don't know, 20 endurance durations, which is like a requirement I've seen thrown around. how do you quantify like the number of rotation of or the amount of reversing moment loads that you get on the tire? It's relatively difficult. Like your car undergoes different corners, which results in different lateral loads. The normal load is constantly fluctuating everywhere, and it's really complicated. And then you have to convert all of that back to what your bearing sees in terms of moment, axial, and radial load, right? So this is one example of where I'd argue that defining the requirements or selecting the bearing and materials is a lot more difficult than the actual selection itself. So most of the work goes into that aspect of it. And there's also other weird considerations you have to take into account. Like there's actually a relatively high amount of bearing losses that you get just in terms of energy on your vehicle. So when you have your wheel which is rotating so quickly over such a large duration, the amount of damping forces from the grease in your bearing actually scales with the velocity squared, right? So you can lose a lot of energy from the bearings themselves. And you kind of see an interesting example of this in F1. They used, instead of us, they used angular contact bearings as opposed to tapered roller. So angular contact in general can support smaller radial loads, smaller moment loads. Basically, it's worse for stiffness in most of these metrics, but yet F1 teams choose to use it. Why? Because they're operating at speeds that are, maybe like 4 to 5 times like what we ever go. So their consideration of losses and fuel consumption are suddenly much more important than stiffness, right? So even in the same kinds of systems, this can manifest in really different ways. So obviously we could go to angular contact, but there's not as much of a benefit as maybe an F1 car has. I mean, they're dealing with larger loads too, yet they choose to use this bearing because that one requirement is so important. So that's like kind of a niche example. But you kind of want to think about all of these things before you go into selecting any kind of costs or materials component. And this, extends like beyond machine elements. Anyways, back to the bearings. You'll typically get 2 ratings. They commonly label it C0 and like C10. So C0 is what's called the static load rating. So this is like if my bearing has some kind of static load on it, even while it's rotating, this is what you want to use. And typically this is conventionally just the radial load. Manufacturers will give you formulas on how to convert like a moment load into a quote unquote equivalent radial load. So you'll take all of your loading conditions, use those formulas, and generate an equivalent radial load. And that static radial load is what you can first look at, and you want your bearing to be under that to whatever safety factor you have defined. The other load rating, as I alluded to earlier, is the dynamic load rating. How well does it handle these loads over time? So there's also another formula that you can use on how to convert these different stresses. But at the end of the day, you'll basically be looking at an equivalent static radial load rating or dynamic load rating. And the other constraint is obviously your size. Okay, so last thing I really want to cover today is fastener preload. So this is, I think, probably the most important yet neglected aspect of mechanical design on the car that I've seen. So in general, people kind of think of fasteners as just a way to like connect 2 parts together, and that's basically what it's doing. It holds 2 parts together. But the design considerations that you have actually can be relatively subtle. So some of you might be familiar with the term fastener preload. So you have something called torque wrenches. If you've ever changed a tire, you kind of have an idea that you want to torque it down a certain amount, and these preloading torque wrenches basically just serve to consistently torque it down. What people don't realize is that that amount of torque can really be the difference between failure or success of your system, right? So let's say I have 2 plates and I want to clamp them together, and they have a shear load. So they're basically trying to move in this direction. A really common pitfall is, oh, I'll just throw a fastener in between it and put a nut on the other side, and it will prevent these 2 plates from sliding together, right? So as we talked about in materials last week, the shear strength of materials is typically a lot weaker than the normal strength or the tensile strength. So in this case, it's bad because you're shearing the fastener. And the first piece of advice you ever hear when designing fasteners is, oh, don't shear the fastener. And that's correct, right? You don't want to be loading these relatively thin interfaces right here in shear. But this is an example of where fastener preload can really change the way that you approach the system. So let's say I didn't torque this fastener down much. If I were to pull these two plates apart, they basically just shear the bolt interface, right? But the interesting thing is that you can actually preload these screws a lot and clamp the plates together. So now you actually have another way to react that shear load, and it's the friction between the two plates themselves. So if I wanted to react that shear load, if I preloaded it enough to where the friction is enough to resist the shear force, then my fastener actually no longer ever gets loaded in shear. Its only purpose is to clamp the two plates. And once they've been clamped sufficiently, then I don't need the fastener to support shear loads. So in this instance, if I don't preload enough, if I don't provide enough clamping force, then those two plates aren't going to have enough force or strength to resist the shear load from the friction, right? So that's one instance of where it's really important to preload the fastener. So yeah, that's one example of why it's important. And we're going to talk through, I guess, some of the actual mechanisms behind how fasteners work. So if you look at the left side of this image here, you have two materials, this lighter gray material and this darker gray material and a fastener. In this case, they just have a nut on the other side that supports this bolt, right? As you tighten the bolt more and more, you develop an axial force along the bolt that compresses these two systems. And no material is infinitely stiff, so you have deformation of both the bolt and the material, and that's demonstrated by how you have the string here and within the material. So because of those two stiffnesses, the final deflection of your system is dependent on both the stiffness of your bolt and the stiffness of the two materials you're trying to make together, right? And that's relatively important in terms of defining something we call the joint strength of the system. So after you preload it, you have two sets of forces. You have a preload force from the bolt compressing the two metals together, but you also have a normal reaction from those interfaces pushing the bolt outwards, right? So the bolt is in tension in this case, and the materials are in compression, equal and opposite. But if you look at the plot on the right-hand side, they don't necessarily deform in the same way. So you can see that the member or the two plates here has a much steeper slope when you plot the force versus deflection than the bolt. And that's because the stiffness of the material is different. So when you pull on this bolt, something that you really care about is obviously how stiff is the system. If I were to attach a load to this a darker gray plate and pull on it, how stiff is the system going to be? And it turns out the answer to that is it's a combination of both the stiffness of the bolt and the material. But the super unintuitive thing is that it also depends on your preload. So there's something called joint stiffness that I talked about earlier, and that joint stiffness is actually dependent on the amount that you torque this bolt down. So larger torques and axial preloads on your system aren't just good from the point of like holding two plates together to react to shear load. It's also good because it can increase the stiffness of your system. Now, the equations for this can be a little involved. So if you want to reference it, there's a QR code at the beginning, which links you to Shigley's, the textbook, and they have a relatively good way of showing you how to assess the shear load, or sorry, the stiffness of your fastener joint. Okay, so I couldn't really find an image in the textbook for this, but another really important aspect of fastener design is basically how to size your fasteners and how much to preload them, right? So in general, most of the times you want to preload a fastener as much as you can, and you can have one of two ways that the system can fail. Either the fastener that you use has threads that are weaker, so the fastener threads literally pull apart, or the mating material, what you're threading into, in this case that would be the nut, has a weaker material, so that fails first. More often than not, it's always going to be the material. Your fastener is usually made of a relatively hard and high yield steel, whereas your material might be something like aluminum or a softer steel. So the lower of those two strengths is basically the most that you can preload the system, right? And when you bolt into a thread, the threads actually don't distribute the loads evenly. So if I have a mating thread and a fastener, the threads at the bottom of that, at the bottom of the mating material, in this case, the nut, this bottom part is loaded a lot more highly than the top part. And it's a little counterintuitive, but the reason behind it is that both systems have variable stiffness. So you can kind of imagine the fastener as a really stiff spring, and you're attaching that spring to the other threads of the mated fastener or the mated thread. And because those two springs don't have matched stiffness, the load on the bottom tends to be more. And so the thread is always elongating, the fastener is always elongating when you fasten it, and the material is always compressing. So that combined action and the stiffness differential is what causes the bottom threads to be loaded more. So the way that you calculate that tear out strength, as they typically call it, is by viewing these two surfaces as cylinders. So you have one cylinder within another, and you're basically pulling up on this as you preload it, right? And the strength of your system is the shear strength between those two interfaces. So you can kind of model this as, I guess, the amount of area that you have exposed. Like if you were to take a cross section of your thread and see where that cylinder cuts through the thread, that area is where you're loading it. So in practice, more often than not, this is done empirically, and there's a formula that you can use to determine the failure point of the thread. And we actually have, do we have an updated calculator for that? Okay, cool. So yeah, we have a somewhat sketchily validated calculator for you to compute these loads with. And I haven't linked it here, but Robert can show you guys if you want to take a look. But basically, when you have these fastener interfaces, generally the larger your fastener and the larger the mating thread, the larger the strength of it is going to be, right? That makes sense. So that's one parameter. And then you also have the relative materials of the mating thread and the material or the fastener. But another consideration is also actually the threads and how they're distributed. So in general, if you have smaller, finer threads, but you have more of them, they're going to distribute the load better than larger threads. So all of this gets factored into the calculator, and it spits out what's called a proof load. So the proof load is generally the highest axial force you can generate with the fastener before either the fastener or the material that's mated to fails. So this proof load is really the most important parameter of designing any fastener joint, right? Again, if I have two plates, knowing that proof load allows me to calculate how much shear friction I can develop, which is a really common way of using fasteners. And the interesting thing is that it's dependent on the bolt torque. So as we tighten this bolt, like obviously the system compresses, but how do you relate this torque on this surface to the amount of axial force that you have in the system? So that's also somewhat complicated, but the mechanism here is as you tighten this bolt, you have two torques that originate. You have the torque from the friction between the thread and the mating material. And that friction causes a torque that resists you turning the bolt more. But you also have the friction between the underside of the bolt head and the material. So that's kind of like a circular friction right between the surface of the bolt and the material. And that also reacts your torque strength. So again, you can correlate that torque to the amount of preload. And essentially, like it's mostly use of this calculator, but you choose different combinations of these thread sizes depending on what kind of constraints you have in the mounting pattern of your system. And once you choose that thread size, you can go and check, is this proof load actually large enough? If not, then I have to upsize my fastener or redesign to have more fasteners to generate the correct amount of proof load in the system. And from there, you look at the calculator, and the calculator tells you how much proof load you can generate before either of the threads fail. And once you have the proof load, you can back calculate based on these friction values, the actual amount of torque that you need to turn the fastener. So torque is the most common way of detecting how much axial load you have in a fastener, but it can actually be somewhat like imprecise. Like a lot of torque wrenches that you use are like plus or minus 25%, which is like kind of an absurd number, right? Like you have this really sensitive joint and like the variance you have is plus or minus like 25%. It's kind of crazy, but there's strategies that people use to assess, I guess, the failures of these systems where you lose this preload. There are some vibration measurements that you can do where, for example, you vibrate the light gray material and measure how it propagates to the other end of the fastener. And because the vibration propagation is dependent on the amount of stiffness or preload that you have in the system, you can actually assess if your system is still properly preloaded. And this is actually like a really large area of like acoustic analysis that you see in manufacturing warehouses. And sometimes they'll even have like microphones just near a machine. And if they hear like a slight difference in the frequency distribution, they'll be like, oh, something's wrong. And typically, more often than not, it's like a fastener that's unloaded. So the most important way of retaining a fastener is the preload. And there's a couple other things you can do, like Loctite, if you guys have ever heard of that. But it's not like a fix-all solution, right? In general, you need to retain your fastener by hitting some amount of preload. And if you're not tightening it properly, the fastener can also just back out, which is a really important consideration. FSAE has rules on what they call positive locking as a result of this. So that's, for example, where you have some kind of wire going through the thread and wrapping around something else so that it's not physically allowed to rotate even if it comes loose, right? But in general, you should try to design so that you don't rely on those type of things. You want to maintain that preload so that your fastener joint is predictable. A really good example from last year is on the hub, we have what's called, I guess, a minimum preload that you need on the bearing. So if we go back to this slide, most bearings aren't just, by Kevin, most bearings just aren't drop-in usable. There's some kind of loading requirements or mounting requirements that you need for the system. So for example, in this, we'll use a straight roller bearing just because it's easy. There's usually some amount of tolerance between the rollers and the rings that you have. So there's space between the rollers and the rings. And I mean, that's partially because they can't hit those tolerances well enough when they machine these elements, but also because if I'm inserting a shaft and I'm doing something like a press fit where it deforms the housing, then I don't want to immediately load my bearing elements with that press fit, right? So you have this slight mismatch in the spacing of these bearings. And what you're actually supposed to do is something called preload. So what preload means is that you actually apply a small amount of load to the bearing to begin with. And what that does is it gets rid of that free play and it compresses the bearing slightly. So it's like a combination of the best of both worlds, right? You have the small amount of tolerance so that you can do press fits. You don't have over constraint in your bearing. And then you apply a small amount of load of it to get rid of that, that play. So typically that's really commonly done with fasteners, right? So imagine I have a fastener that pulls one material this way against the inner ring and the opposite direction against the outer ring. That's what you call an axial preload. And those amounts are typically really sensitive, or the bearing operation is really sensitive to how you axially preload it. So it's important to design your joint interface to be able to provide the correct amount of preload. And what actually happened this year is that on our front hubs, you have this, the front hub bearing and the hub rotating in it. And there's a fastener bolt that preloads the two together, right? But it turns out the preload amount was super small. So what they did was they used a lock nut and they just, tightened it down to the right torque. And we're like, oh, we've got the right amount of preload. But when you're not preloading your fasteners sufficiently, even though we were hitting the right amount of preload that we wanted on the bearing, they're not basically just back out over time because the system vibrates so much. So it's actually like a really complicated problem sometimes. You have this combined requirement of you usually want really high torques to be able to prevent your system from loosening, but also sometimes you want to generate really specific amounts of axial load. And the most common case is a bearing configuration. So in general, when you're designing fasteners, selecting them, you should recognize these two things. I want to produce some kind of amount of axial load. But at the same time, there's all these considerations of like the joint strength I need to consider and how stiff the joint is. So that all kind of goes into play when you choose the fastener. Yeah. So those are the main things I wanted to cover today. I gave some examples of how material selection, fasteners, and bearing selection kind of plays into the different areas of the car. So I figured for our last bit of time, do any of you have like examples of like materials that you're confused about when you're learning about the car, or fastener interfaces that don't make sense? Which lugs? Like that constrain the wheel to the hub? Well, that's wrong because wait. That's wrong. Yeah. I think he's lazy because he doesn't want to look for the large torque wrench.
Pretty sure that was the exact. Pretty sure.
No, because I've definitely preloaded it before. But like that's a good question. Like, what do you do when the the two materials are different. Basically, you just get a different friction coefficient between the two materials, and the weaker material, in this case, I think it's the nut, that just fails first, right? So you preload to whatever amount of proof load that the nut can handle.
Good question about exactly what you're talking about. So this year we're doing center lock.
Mhm.
So we're gonna make the center lock nut titanium and thread it onto the hub. What are your thoughts on that?
Well,
I know I talked with Kieran, and combustion's also gonna be the same.
okay, well, you tell me, like, why would you want to select titanium over something else if you're doing a center lock?
I believe it's like the interface between the materials and what you were talking about, and how like there's a less chance of it failing.
Less chance of failing. So that's like a very generic requirement, right? So
I had it written down.
so these all relate back to like the really basic questions that I presented here. So see if you can like frame the problem in terms of why. You know, well, do you know why is that rule there? Like the center lock? It's not yield. Well, you're actually right, but it's not, I don't think, oh, okay, fine, I'll give you that one. If you have high pressure between the two materials, yeah, you can get galvanic corrosion if there's not, you know, yeah, it's just for hardness. It's not really for, okay, so why do they tell you to anodize it as opposed to like heat treat it so it's harder? That's a good question. Like, yeah. So why not just make the material harder? Like, why are we anodizing it? So you don't with anodized. It's like you know those Japanese swords that like we talk about where like they're flexible but like still really hard on the outside? It's like kind of the same thing. When you anodize the surface, you produce a really small layer of oxide on it that's like ceramic. So that interface is relatively hard, but the inside is still somewhat ductile. So the reason that matters in a center lock is you have a lot of vibration going through it, both radially as well as like supporting the moment load. So you don't want it to be brittle, like that would be really bad. So you get the benefits of, as you said, the galvanic corrosion because you don't have a metal on metal interface, you have ceramic. But you also have the fact that it won't gall or damage the surface because the surface itself is hard. Oh, what's the Fastener requirement again? Yeah, because I mean, like if they see a damaged surface, they're gonna know like you fucked it up in some way, right? Yeah. I don't know. You tell me why is no, okay, you are allowed to do titanium. But why would you want to do titanium? Oh, come on, you should know this if you're choosing it.
No, well, that's what they want to do this year.
Okay, I'll give you a hint. Left flop. So why does it say that if steels are stronger than titanium, right? Okay, what kind of stiffness difference is there? Well, that just sounds worse in every way. You have worse yield strength, worse stiffness. So like, why would we choose titanium? Lower, okay, sure. Yeah, okay. Well, there you go. It's like just the density, right? But is that like your only requirement? Like, well, what other things are you thinking about when you choose titanium? Well, how are you thinking about them? Is it weight and strength the two common requirements that every LHR system has? See, I called it. I know, but the discussion about the anodization is interesting, right? Because that's like a somewhat unintuitive requirement, but it relates back to hardness, which isn't something that you would think about. So if you're doing center locks, the two really sensitive things are the fact that that thread at the end that you're locking onto is both loaded extremely highly axially from your preload, right? You need to push the system together with a lot of proof load. But at the same time, you also have the axial load from the tire going through the thread. And all of this is concentrated on that thread. So like you can see, it's a lot more complicated because now you have actually moment loads on the thread as well, because that's how it transmits from like or part of that is like the transmission from the tire to the hub, right? So it's like that thread interface, which basically dictates like the material selection for center locks. And frankly, like I don't even know everything about it, but do you remember the broken center lock combustion head last year? So they used the cotter pin to basically retain the nut. What they didn't realize is they actually preloaded it too low. So the amount of friction wasn't holding that nut or the castellated nut on that surface. So part of their load, their torque on the hub was actually being transmitted to the cotter pin, and that like sheared the interface where it locked against the nut.
What do you mean by like harder thing? You're talking about cell?
Let's see.
Is there three? Are you talking about the 3000? Or are you talking about something else? I feel like you're talking about the Dalton.
You said 3?
Yeah, usually like 3 to 4. And I'm pretty sure combustion used only 1 last year, but usually teams use 3.
We might be talking about the same thing.
I think you're talking.
You're talking.
It's the things that go into the hub and then they lock into the rim as well.
Hubs, then
Yeah, they're on the hubs, and there's an interface for them on the hub that we're gonna have to make, and then it goes into the rim as well.
okay, yeah, I think it's the same thing.
I think.
Yeah.
Oh,
Yep.
I have one more question. So,
Mhm.
what about determining the size, the thread on the hub this year? Like, what's so
The size of
whether you
what?
want a smaller thread size or like
Oh, thread. I think the thread size is basically dictated by your bearing size, right? So that's
oh, no. I mean like the actual threads. Like obviously the
like on the center lock, right?
Yeah.
Yeah, I understand that. So like your thread can't be bigger than the shaft that you put through the bearing, right? So it's driven by the bearing size. You basically make the thread as large as possible while still being able to fit it through the bearing.
that's what I was.
Oh, the pitch. So pitches typically come for a given radius. They come in like 2 sizes, coarse and fine, and you'll see this referred to as UNC and I think UNF. Is that it? I don't know. But there's typically just like 2 thread sizes, so like different thread sizes per radius. And honestly, like it just depends. Like if you want better load distribution, you would choose the finer threads. But if you don't want to have to spin your fastener a million times, then you choose the coarser thread. You remember the thing where I said the bottom threads are loaded much more heavily than the top threads? Yeah, it's exactly that. So if you have a lot of fine threads on the bottom, they'll be able to distribute that pressure better as opposed to just like one large thread. Yeah. So for something like center locks, like we would probably want to make it relatively fine. Like we don't really need to be taking our wheels off at lightning speed, which is like kind of my argument against center locks to begin with. But
well, wait, you know why we're doing this here?
I guess I haven't.
We got these grips that are like 1.6 pounds lighter on each assembly. Yeah, the magnesium on the ready.
And you have to do center locks to fit them.
Yeah, they don't have any. They don't have four.
I guess I'll just tell you, like center locks still scare me, and I feel like
I
I'm
have no clue. To be honest, so
like you've got like one huge ass thread that you machine yourself and treat yourself, and like if it fails, like your driver dies. Well, maybe not that, but yeah. Whereas like 4 bolts that you know the strength of relatively well.
No,
Yeah.
Kieran was saying the same thing, but because of those rims, it's kind of worth to switch. At least that's the decision that he came to. I mean, the other remote paper is flat out worse. The only benefit then is that you have. Preload.
Yeah, I mean, for that, I mean, the question I would ask is like, how you, if you're confident enough to machine it, because I don't think I am.
We're gonna outsource it.
Oh, okay. Ooh, Waken can definitely do it. I believe in Waken. Oh, there's also different types of threads. So for this one, they use something called a buttress thread. It's a funny name, I know, but the thread basically isn't symmetric and it like angles a lot more in one direction because it supports the load better. It's different joint.
What's the other kind?
I don't know. I only know about the buttress one. Buttress and whatever you call the standard one. But combustion, I'm pretty sure did buttress threads last year, so you can ask Jonathan. I think about it. Okay.
They somewhat knew what they were doing, so.
Yeah. Hey, I mean, they still had a lot of grief with it, like
Yeah.
installing the wheels and
They
stuff.
had a
So
lot of issues.
are they still doing it this year?
So the way we did the rims, we're doing it order like together. For that.
Okay.
We're all using this.
I'll go ahead and start the recording, but. Yeah, I don't know. They scare me.
Oh, yeah, me too. I'm like making